اوكي، السلام عليكم ورحمة الله وبركاته. أسعد الله أوقاتكم بكل خير. Today inshallah we are going to have the third lecture in our course for Instrumentation and Measurement 1, and in this lecture inshallah we are going to start the new chapter, which is chapter 5. As we mentioned in the previous lectures, in the course objectives, that we say the course objective is to study some basic concepts for some physical quantities or some parameters, okay, and study how to measure them using different instruments. Now we started with the chapter 5, which will talk about the pressure. So in this chapter we are going to study basic concept in the pressure, and solving some problems related to the pressure, and at the end of the chapter we are going to study some different measuring instruments which measuring the pressure. So let's start with the today lecture, which is the first part of the chapter. And before we start, we already discussed and you agreed to have the quiz as a direct contact quiz or quiz in classroom, okay, instead of online quiz, and it will be in week 6 as we are already agreed. Each section will have their quiz in their time of the lecture, and they should come starting at 5:30, and then if all students came, we will divide inshallah into 2 groups. Each group will have a quiz for half an hour. Okay, so starting with review whatever we have done last lecture. So in lecture number 2 we studied the representation of derived units in their base units form for the international system, and we know how to analyze and express most of the derived units in their base units form. The second section was talking about the instrumentation terminologies, and we studied different terminologies that is needed to be studied for any instrument devices. And last, we talk about the properties of materials, okay, and we discussed the differences between mass and weight, and how they most of the students they misused or confused about differentiating between these two quantities. In addition to that, we studied the density, specific weight, and specific gravity, and these 3 terms, which is again related to the mass and weight as well. It's a very important, and we are going to use it a lot during this chapter and the next chapter. So I put it red line, okay, in red color, to show how important it is. Please, before starting this lecture, okay, and if you haven't understood these properties in the last lecture, go through it again. Try to study it hard, okay? Try to understand it before starting this chapter. So let's start with the outline of today's lecture, inshallah. In this lecture, we are going to have some introduction and principles with some formulas with units for pressure, okay? The second part, we are going to take the types of the pressure measurements, and we are going to see that we have 6 division or 6 types of pressure measurements. And the last thing, we will take some application of pressure or some pressure measurements for fluid, which is called the hydrostatic pressure. And we know that the meters, it has 3 phases: solid, liquid, and gases, okay, and the two status, okay, which can flow is the liquid and gases. That's why we call it a fluid. So once you hear the word fluid, it means that it's either liquid or gases. In this section, we will talk, inshallah, about the liquids. So we will study the pressure of liquids. Okay, let's start. Pressure. So in the starting, we'll take an example, okay, in order to understand the concept of the pressure. So let's start with the famous example as the hammer and nail, okay, hammer and nail. Now, if you want to stick this nail, okay, into a wall, you need to apply a force using this hammer, okay, in one of the side of the nail. And in the nail we have two sides. One is the flat side, okay, which has a bigger area, which is this one, and the other one is the sharp side, which has a very small area. Now the question is which side you are going to use, okay, which side or which way you are going to use. Would you apply the force of the hammer on the flat side or on the sharp side? And which side again will be sticked on the wall? Is it the flat side or the sharp side? Well, I think most of you will know, okay, the correct answer. And the correct answer is you will apply the force, okay, into the flat side, right? And the sharp side is pointed to the wall, and it will punch a hole and stick into the wall. Now the question is why is that? Okay, why is that? It's a very simple answer. Because the sharp side, it has a very small area, which in turn it will generate more pressure. So as long as you have a very small area with the same force, you will get a more or high pressure greater than that pressure of the greater area. So what's the definition of pressure? Pressure, it's the amount of force applied to the surface of an object per unit of area. Again, it's the amount of force, how much force, okay, you apply into a surface of an object, okay, or into an object per unit of area, So two things is important in the pressure. So the pressure is a function of the force, okay, and the area, So the formula can be written as pressure is equal force over area. And in other words, we can represent, or we can say that the weight, it's another form of force, or let's say special type of force, which is related to the gravitational force, okay, gravitational force. So instead of taking the general acceleration in the force, mass multiply A, you will say here in the weight, mass multiply G, which is related to the acceleration of gravity. Now, what are the units? Okay, what are the units of the pressure? Well, the units of the pressure, as we can see in the formula, that in the numerator we have the force, okay, so the SI unit of force is Newton, okay, so the Newton, it's the SI unit of force. Now what about the area? The area, it's a square, okay, square of any length unit. In SI we are using the meter as a length unit, so we square it and we will have a square meter, okay, square meter. So whenever you see Newton per square meter, it is exactly the same as Pascal. So Pascal, it's a derived unit in the international system, which is equal to Newton per square meter. Sometimes you will see the kilopascal, okay, so kilopascal, it's simply that instead of Newton you just write kilonewton. Now what's the relation between the two? It's a very easy. 1 kilopascal, it's exactly equal 1 times 10 to the power 3 Pascal, okay, 10 times power 3 10 to the power 3 Pascal. Now what about the English system? Okay, what do you think? In English system, the force or the weight has a unit of bound force, okay? The force or weight has a unit of bound force, as we discussed in the previous lectures. Now, what about the area? Area, it could be, we said that it's a square of length units. So it could be inch or it could be foot as a length unit, okay? So you take the square of this length unit. So sometimes you are going to see square inch, okay? And sometimes you are going to see square foot, okay? Now, not all the time, okay, you are going to use this expression as a pound force divided by square inch. Now, if we take the name of the unit, you're going to say pound, okay, per square inch. So if you take the initials, okay, for each word of the unit, you will get a PSI. So again, whenever you see the word PSI, it means exactly a pound per square inch. It is exactly a pound per square inch. Now, what about pound per square feet? Instead of I, you will write F, so it is a BSF. It is a BSF. Now, is there any other units? Unfortunately, yes. Okay, so we have different units in pressure, and this expression shows the different units of pressure and how they are related to each other. So all of you, Shabab, need to uh, know this relation, okay? So if you are being asked, this will not be given, okay? So at least you should know and memorize this relation for pressure units. Okay, now what's the relation between pressure and area? What's the relation between pressure and area? Now, in the previous example for the hammer and nail, you choose the side, okay, that the hammer will apply the force on the flat side, which in turn the sharp side will be pointed to the wall, okay, will be pointed to the wall. So why you choose the sharp side to be stuck in the wall? Well, the pressure is inversely proportional to the area of the surface. It's inversely proportional to the area of the surface. What do we mean by inversely proportional? It means simply that pressure, it's proportional to the inverse of area, okay? To the inverse of area. So that means as the area decrease, okay, as the area decrease, so if the area decreases, okay, what will happen to the pressure? It is simply increase because they have inverse proportion. Now, is there any application, Shabab? Is there any application for some high pressure needs? I mean that, is there any application that we need to have high pressure? That's why we choose small area. Yes, it is the same as we have in the first in the introduction of the lecture, which is the hammer and nail. So in the hammer and nail, okay, you need a very small area to get more pressure, okay, to get more pressure. So if you apply some same force on flat and on the sharp side of the nail, okay, you will get a different pressure between both, and the higher the pressure it is with the sharp side because it has a very small area. Now, any other example? Yes, we have the knife, okay, this is the knife. So sometimes you will see that both sides they are equal, but actually it's not. If you just look carefully to the knife, you will see on one side it's a very sharp, okay, it's a very sharp, and the other side is not. So this is very small area will generate or exert more pressure when cutting the things with same force, okay, with same force. Now, sorry. Now, in the other side, do we need some application that we need to apply some low pressure? Yes, of course. So as the area increase here, which is the vice versa of the above relation. As the area increase, we know the pressure will decrease. So an application for needs for low pressure is the walking on the snow. Okay, walking on the snow. So if you just walk with your simple shoes, your weight, okay, your weight will generate a force, okay, according to the weight of your body on this small area, okay, on this small area which is your shoes. So the pressure will be greater and you will sink down, okay, you will sink in the snow. However, if you want to walk on the snow, you need some shoes called snow shoes. Now, why they call it snow shoes? Because they designed it, okay, to have a very large area compared to your shoes. So see, this is the shoes. This is the simple shoes, okay, and that is the snow shoes. So compare the area. It's maybe double or triple the area of the simple shoes. Now, since we have a very a greater area, so it will exert low pressure compared to your weight of the body of your body. Okay, so maybe you will not sink down. Maybe you will not sink down. Another example is the army tank. Okay, now in the army tank we can see that that the wheels, okay, the wheels of this tank, it is on the steel track, okay, it's on the steel track. So the army tank moving on the ground by the steel track. Now, why they build it or designed it like this? Well, it's easy. Now the wheels now it's not touching the ground, so there is no direct contact between the wheels and the ground. Why is that? Because they have a smaller area than the whole steel track. Okay, so the track contact area on the ground is much greater, okay, than the wheels contact area to the ground. Again, the track contact area with the ground, see, all of that is much greater than the wheels contact area on the ground. So it will exert a less pressure, okay, on the ground. Now that's about the relation between pressure and area. Now let's take some examples, okay? And the first example, of course, it's a unit conversion, okay? So it says convert the following pressure units or express the following unit in or express some unit in the following units. So it might have different words, okay, but the meaning is the same. It's the conversion. Now the first one, I will solve the first one and I will let the rest for you to practice. Now the first one, it says convert 48 psi into kilopascal. Now, as you can see in the bottom of the slide, you can see the relations between the units. So what we need to pick the relation between psi and kilopascal. So here we have 100 kilopascal. Okay. 100 kilopascal is equal 14.5 psi. Okay, 14.5 psi. Now we have, as we studied in the unit conversion for lecture number 1, we have our initial value, which is a 48 psi. Okay, and then we multiply it by the fraction of the relation, okay, which we can then cancel the psi unit and keep the kilopascal. So in order to cancel the psi, we need to put it in the denominator and put the kilopascal in the numerator and just copy the values of the relation. So here we have a 100 kilopascal, and here we will have a 14.5 psi. Now, as we can see that we can cancel the psi from the top and bottom, and the answer is exactly equal to 331.03 kilopascal. Okay, kilopascal. Some of you will say that there are some other ways, okay, and actually it's exactly. They said we have the we can put the units below each other, okay, so we'll put the relation on the top, and we'll put whatever we need to convert on the bottom, okay, in some pattern. And then we can make the cross multiplication and find the value for the unknown. So simply they say it like this. So write the relation. So they can say that whatever we have the relation, we have 100 kilopascal, okay, equal 14.5 psi. So this is, we write it in the first line, and the second line we write in the same pattern. We have a kilopascal equal psi. So we have here a 48 psi, and we have unknown kilopascal. So by cross multiplication, okay, so you multiply the x by this side and the 48 by the other side, you will get what? You will get 14.5 x equal 48 multiply 100, okay, which in turn, in order to get the value to solve the equation and get the value of x, you will divide both equations by 14.5. So you multiply 48, okay, multiply 100 divided by 14.5, which is exactly the same as what we have done on the top or in the first part, okay? So it's exactly the same, and you will get the same answer at the end, which is the kilopascal value, okay? So try to answer I give the final answer, so try to practice and match your result with the given answer. Now, next example on the second slide, okay, or in the next slide, it says you have been given a figure, okay, and this figure has some box, and this box has been put on the table with two position, okay, with two position. The first position vertically and the second position horizontally. Now it says in the given information that the weight of the box is 100 Newton, okay, and the area for the horizontal side is 0.1 meter square, and the area for the vertical side, okay, this one is 0.01 square meter, okay. So the horizontal one is 10 times greater in the area than the vertical one. And the question said, find the pressure exerted or applied by the two boxes on the table, okay, by the two boxes on the table. Well, let's say box number one, okay, we will solve for number one, and we'll say that we have a pressure is equal, writing the formula, weight over area. Now we have the weight as 100 Newton. Try to write the units, okay, within your solution. This is divided by 0.1, and this is the area, which is square meter, and we said that a Newton per square meter is equal Pascal. So the answer here, we can say that it is equal 1000 Pascal, which is equal 1 kilo Pascal, okay. So this is the pressure of 1. This is the pressure of 1. Now the second box, okay, the second box, we will write again the same formula, which is the weight over area, okay, and we can say that the weight here, it is the same, 100 Newton, divided by Now the area is smaller, and we know that as we get smaller area, the pressure will increase. Okay, the pressure will increase. Now we will compare. Now here we have a 0.01, okay, 0.01 square meter, and the answer now is not 1,000, it is a 10,000. Why is that? Because we said that the area of box number 2 is smaller by 10 times than the area of the box number 1. That's why we get a greater pressure 10 times than the pressure exerted by box number 1. So this is simply the relation between the pressure and area. So here we have 10,000 Pascal, which is exactly equal 10 kilo Pascal. Okay, 10 kilo Pascal. We divide by 1,000. Same as the top one, divide by 1,000. Okay, so this is related to the example number 2. Now example number 3, it says, what will be the mass? Okay, he asked about the mass, not the weight. What will be the mass, okay, of an object in kilogram and pound mass if it applies a pressure of 1500 Pascal on a table? Okay, so what you have, first, the problem is the mass of object. So first you write mass of object. This is the problem. Okay, this is what we are trying to find. Now we know that it's given the pressure is equal 1500 Pascal, which is Newton per square meter. Okay, and that's it. On the right bottom corner, okay, here you can see a relation between the bound mass and bound force with the SI units, kilogram and Newton respectively. So here, where we can find the mass, okay, do you know any formula that contains a mass? Yes, we have two formulas. We have the formula of density, which is saying density is equal mass over volume. Now in this case, we don't have the density, we don't have the volume. So I think this is a not good formula to be used to find the mass. Now any other? Sorry. Any other formula? Yes, we know that mass, it is in the weight formula, and the weight we can say it's M multiply G. Okay, M multiply G. Now, do we have the G? Yes. The mass, it is the one that we are going, or we need to find. Do we have the weight? No, but the weight we know, okay, that we can find it in the pressure formula. Okay, we know that the pressure is equal weight over area. Okay, weight over area. Now, sorry, now I think the question is not complete. Okay, the question is not complete. Here, instead of an object, let's say no. Let me say the area is given as, suppose that the area is given as 0.1 square meter. Okay, suppose that the area is given as 0.1 meter square. This should be given in the question. Okay, this should be given in the question. Now in this case we have the area and we have the pressure. So this weight, we can solve for weight, and then after we solve by weight, we can substitute it in this equation and then find the mass as weight over G. Okay, weight over G. Now let's try to solve it. Here we have weight, it's equal pressure times area, and we know the pressure is 1500. Okay, so we write 1500 Pascal, which is a Newton per square meter, times the area, which is a 0.1 square meter, and 1500 multiply 0.1. Here we can see that we can cancel the square meter on the top and bottom, and the answer of the weight is simply equal 150 Newton. Okay, 150 Newton. So this is a one part of the answer. The second part, we will take this weight, okay, and then substitute it in the weight formula to find the mass. So mass now equal weight over G, okay, weight over G, and the weight is equal 150 Newton divided by 9.81 meter per square second, which is equal 1.56 kilogram. Okay, 1.56 kilogram. Now, according to the question, he asked you to find the mass in kilogram and pound mass. So you can find you can convert the unit of the mass, okay, using this form, this relation. And another way, I think I have told you that, or we studied that in English system, okay, in English system, I will write a note here on the right side. In English system, we say that 1 pound mass, okay, will give a weight of exactly 1 pound force. Now, where is the acceleration of gravity? The English system, okay, plugged the acceleration of gravity inside the unit of pound force. So inside the unit of pound force, there is a multiplication of the acceleration and of gravity, so that you will get the same value between the mass and weight. So here you can convert this weight to Newton directly using the second relation, okay, of the pound force and the Newton, and this is exactly whatever you get in pound force, you can say it is equal the same value but in pound mass, okay, in pound mass. So try to solve it in both way, okay, and compare the answer. It must be the same. It must be the same. Okay, now that's all about the examples of pressure. Try to solve most of the problems in the book, okay. So as you can see here that there are around 20 problems at the end of the chapter, okay, which is page 82. Try to solve whatever you can, okay, as much as you can, and practice to get familiar with the formula and the type of questions. Now the next section, we will take the types of pressure measurements, okay. Now sometimes we are using different types for measurements and reading the pressure. The first type is called the total vacuum, okay. The total vacuum is simply the absolute zero. So there is a zero pressure, okay, zero pressure. So you suck all the air particles, okay, in some place, and you will get at the end the zero air or zero pressure. So that is called a total vacuum. Now where can we find this total vacuum? It's in the outer space, okay, في الفضاء الخارجي. Now the second type is the atmospheric pressure, okay, atmospheric pressure اللي هو الضغط الجوي. Now what is the definition of the atmospheric pressure? It is simply from the formula weight over area. We can say it's a weight of air column وزن عمود من الهواء from the atmosphere من الغلاف الجوي up to the sea level. Okay, so up to the sea level we can say that we have a one atmospheric. Now this weight, okay, or the air contains different particles, contains oxygen, hydrogen, nitrogen, and different gases. Okay, so as we go up, so suppose this is the atmosphere. Okay, suppose this is the atmosphere area and this is the sea level. Okay, this is the sea level. Now the atmospheric, it is from the atmosphere up to the sea level. This is exactly one atmospheric pressure. Now if you go up from the sea level, so you become here. Now how much particles of air or how much weight of air is left? Is it greater or less? It is actually greater. Okay, it is actually less. So in this case we can say that as you go up, okay, as you go up from the sea level, which is our reference, the atmospheric pressure goes down. Okay, the atmospheric pressure will decrease, and vice versa. If you go down from the sea level, okay, the pressure will be greater. Now this is a simple explanation for the atmospheric pressure. The third part is the gauge pressure. Be careful يا شباب. Gauge pressure, not pressure gauge. Gauge pressure, it's one of the pressure measurements. Okay, you measure the gauge pressure. Pressure gauge, it's a device. Pressure gauge is just an instrument, device to measure pressure, whatever the pressure. So sometimes this pressure gauge, which is the device, sometimes measure atmospheric pressure, sometimes measure the gauge pressure, sometimes measure some other types of pressure measurements. Okay, so here we are talking about pressure measurements. Gauge pressure, not pressure gauge. So what is gauge pressure? It is any pressure above the atmospheric pressure. So the reference, okay, the reference for the gauge pressure, it is the atmospheric pressure. So the zero, for example, in the previous slide, we said this is the atmosphere, right? This is the atmosphere. So on the top we have zero pressure, which is the total vacuum. So the reference of our atmospheric pressure is the total vacuum. So the zero of the atmospheric pressure is the total vacuum. When I say the reference of something, it means it's a starting point or it's zero. So at this reference, the value is zero. Now, I said here for the gauge pressure that the reference is the atmospheric pressure. So at atmospheric pressure, there is no gauge. Okay, there is no gauge pressure. Any value of pressure above the atmospheric pressure, this is called a gauge. Okay, this is called a gauge. So assume that you apply more pressure greater than the atmospheric pressure. Okay, so this value of pressure is exactly equal the gauge pressure. Now, what about the second type? Is there any value below the atmospheric pressure? Yes. This is called the vacuum pressure. Okay, this is called the vacuum pressure. Vacuum من اسمها الفاكيوم، المكنسة اسمها vacuum. المكنسة وشو وظيفتها؟ It sucks the air. Okay، يعني تشفط هواء. So you are taking some of the atmospheric pressure. You are taking some negative pressure. So that is exactly called the vacuum pressure. It's exactly the opposite of the gauge. So the positive value of increasing pressure, it's called gauge, and the negative value, okay, of that pressure is called vacuum. So negative gauge, it's equal vacuum. Negative gauge, it's equal vacuum. Now what about the total pressure? So now we are talking that we are exposed to atmospheric pressure. So there is some value of atmospheric pressure is on our bodies. Okay, now if someone applied more pressure, okay, we call it gauge pressure. So how much pressure is applied on us totally? Again, if there is an object and this object is exerted, okay, or is exposed by atmospheric pressure. So there is an atmospheric pressure on that object. If someone comes and push that or apply a force, apply pressure on that object, so this amount, okay, this amount of increment or increasing the pressure, we call it gauge pressure. Now the question is, what is the total pressure now on the object? We said it was atmospheric and someone come and make extra pressure. We call it gauge. Now what is the total pressure? The total pressure is simply equal the absolute pressure. الضغط المطلق, okay, absolute pressure. Now the absolute pressure, it is the total pressure applied. The total pressure applied. Now the simple formula to calculate the absolute pressure, if you have a gauge, you will say that atmospheric pressure plus the gauge pressure. So you will add all the applied pressures on any surface of area. Now the last part is the differential pressure. So if two pressures applied in opposite direction, you will take the net pressure or the difference between these two pressures, and this is exactly called the differential pressure, or we call it delta B, okay, delta B. Now see this figure, okay, it shows the relation between the pressures, okay, between the pressures. So let me zoom it in and you can see it clearly. So here we are in the atmospheric pressure, okay, here we are in the middle area. So in this area we have 1 atmospheric, which is equal 14.7 psi, and in this area there is no pressure applied, okay, there is no more pressure applied than the atmospheric pressure, and there is no pressure suck or vacuum pressure. So both gauge and vacuum equal 0, okay, equal 0. Now as you increase the pressure, this area we call it the gauge pressure. So any value above the atmospheric pressure, it is the area of gauge pressure. Now what about if you try to take some of this pressure? It is the vacuum pressure. So here you are taking the negative gauge, okay, you are taking some pressure, not giving some pressure. So here we have a 14.7 psi, so the value that you can take it as vacuum is 14.7, so the total will be 14.7 minus 14.7 vacuum, okay, and then you will get 0 psia. So this area, it is exactly the total vacuum, So here we are in the outer space, or in some area that there is no pressure at all. Now what about the gauge pressure? So suppose that you increase here any value, for example here we have 100 gauge pressure. I'm talking about gauge pressure only, okay, so 100, it is this one only. Now if you want to have the total pressure, what is the total pressure? You will add this atmospheric, okay, so the atmospheric, it is from this point to this point, plus the gauge pressure. So as the formula says, absolute pressure, it is equal atmospheric pressure plus gauge pressure. So in the atmospheric pressure we have 14.7 psi, and here we have an increment of 100 psi gauge, okay, so the total pressure is 14.7 plus 100, which is 114.7 psi absolute. Sometimes you can see in the unit of psi, last letter, okay, letter represent the type of measurements. So if you are measuring only the gauge pressure, you will see that it is psi G, okay, which means psi gauge. So it says that I'm only measuring the gauge pressure. Now if you read the psia, it means this is the PSI absolute. So it means that is the total pressure. That is the total pressure. Sometimes, which is rarely, okay, you can see PSIV, which is related to the vacuum, okay, which is related to the vacuum. Now, let's continue here. Let's take some examples for this section. So the first example, it says a pressure gauge. Now we are talking about the device, okay? We are talking the device. Now he said the pressure gauge now measures the gauge pressure, okay? The gauge pressure. So this pressure gauge measures only the gauge pressure reading as 200 kilopascal, okay? 200 kilopascal. Now it's given that if the atmospheric pressure is equal 14.2 psi, 14.2 psi, what is the absolute pressure? What is the absolute pressure? So clearly it's a direct substitution, okay? So here absolute pressure is equal atmospheric pressure, which is this one, plus the gauge pressure, which is this one. So let us write the given information. Now we have 14.2 psi okay, plus 200 kilo pascal. Now we can add, or what do you think? Well, you cannot add or subtract unless both units are exactly the same, or we call it consistent. Okay, so you cannot add the Pascal or PSI with kilopascal. So you need to convert one to the other. You need to convert one to the other. Even if one is Pascal, for example, here I write on the left side, if I say that pressure is equal 1 kilopascal plus 200 pascal, you cannot say 201. You cannot add. Even we have Pascal and Pascal, but here we have a kilopascal. So you need to convert one to the other. You need to convert one to the other. So in this example, what you will do, you will say that we have 1000 Pascal. So you convert kilopascal into Pascal plus 200 Pascal. Now both units are consistent, and here you can say we have 1200 Pascal. Then you can say it's a 1.2 kilopascal. 1.2 kilopascal. Same thing in here. You need to convert either PSI to kilopascal or kilopascal to PSI. So try to convert it and then find the answer. Now the next exercise or example, it says the absolute pressure. Now it's given the absolute. Okay, the absolute is given here. So the absolute pressure instrument gives the reading as 35.8 psi absolute, okay, and it says if the atmospheric pressure is 0.89 bar, which is this one, calculate the corresponding gauge pressure. So he needs this one. So the answer is simply, since the gauge pressure is unknown, so you will say that gauge pressure is equal the absolute pressure minus, because you are moving this atmospheric pressure to the other side with a negative value, minus the atmospheric pressure. Now try to substitute the value. The absolute pressure, it says here, it's equal 35.8 psi minus the atmospheric pressure here is equal 0.89 bar. The same thing, you cannot add these two units because they are not the same, so convert one to the other. Now let's go to the next section. That's all about the types of pressure measurement. The next section is the hydrostatic pressure, okay, the hydrostatic pressure or fluid pressure. Now, as we explained in the introduction, we said that the fluid pressure or the fluid, okay, it means that any matter, any material, okay, that is flowing. Now, what are the matters that is flowing? We have liquid and gases. We have liquid and gases. The solid, they are not flowing, so they are not part of fluids. Now, in particular, okay, in this section, we will talk about specifically the liquids. Okay, we are talking about the part of fluid which is the liquid. Now, the hydrostatic pressure, here we will study the pressure of liquid, and we will see what are the factors that affect, okay, on the liquid pressure. Now, the hydrostatic pressure, it's a fluid, it is the fluid pressure, and we can divide the word hydrostatic into two parts. The first part is the hydro, okay, which means water, so it's liquid. And the second part, it is static, okay. Static, it means the fluid is at rest, it's not moving, not flowing, okay. If the liquid is flowing or moving, so now we are talking about dynamic pressure. So we will not use the hydrostatic pressure, or we cannot use the formula for hydrostatic pressure. So the first condition to apply the hydrostatic pressure is that the fluid must be at rest, not moving, okay? So it is the fluid pressure at rest, and it usually measures the pressure of liquids when it's not moving, Now let's take an example that we have a container that contains a liquid, and let's say it's a water, okay? Let's say it's a water, and then at the end we'll generalize the formula for the rest of the liquids. But we will take an example as a water. Now here you can see that the container contains a water, okay, with some level. And there is one thing that I need to mention, that for the liquid, okay, the molecules or جزيئات, okay, they are not so close to each other. I mean, in the matter, okay, we are talking the first status is the solid, okay. In the solid, all the particles and molecules, they are bounded to each other, they are so close to each other. That's why the solid, you cannot form it on the other shape. It's difficult to form it to the other shape because the molecules are so close. So it's so difficult to deform it. We call it deform. Deform, it means change the shape. But in the liquid, the particles and the molecules, they are not so close to each other, and in the gases, they are far away from each other. So we will talk about liquid. Now, why I mentioned this one? I mentioned that one because in the liquid, the molecules can be deformed, can change its shape, okay, into the shape of its container. What do I mean? I mean that if you pour some water, okay, in some cup like this, okay, and you put some water right there. So now the volume of water take this shape. Why it takes this shape? Because of the shape of its container. So it deforms its shape into the shape of the container. Now, if you take this volume or this water in this type of cup, it will be like this. The same volume, okay? The same volume. So you'll take this cup and pour it into the other cup. Now the shape of the same volume of water becomes like this. So that's why I need to mention the deformation of the particles of the liquid, and it takes the shapes of the container. Now, let's imagine, okay, let's imagine that we draw this tank, okay, we draw this tank, sorry, the liquid or the water inside this tank into molecules, okay. So let me show it here in the second slide, and here I can show that the molecules of water are not so close together, okay, are not so close. There are some spaces, okay, there are some spaces, and that's why it can deform and take the shape of the container. Now let's for example make it as a row, divide it as a row, and let's say the first row is number 1, so all the molecules are in row number 1, and the second level is row number 2, so these are the molecules of row number 2, and this is number 3, just to make the explanation easier, okay. Now there are 3 things that we need to know in order to understand the pressure of liquids and what are the factors of the liquid's pressure. Now let's look at this one. Let's look at this molecule, okay, this particular molecule، هذا الجزيء، okay، خلينا نركز عليه. Now this molecule, okay, this molecule is braced, okay, this molecule is braced by only one molecule on the top of it. So the weight of this molecule has a weight, okay. So this particle braced or is bracing the molecule number 2, and the word pressure comes from bracing, okay. So when I say it brace, it means it apply or exert the pressure on it. So molecule number 1 has a weight that brace or applied or exert pressure on molecule number 2. Now what about molecule number 3? Now molecule number 3 is braced by 2 molecules on top of it, which is number 1 and number 2. So more pressure. We have now more pressure. Now what about number 4? Molecule number 4, it is exposed to more weight and more pressure than the top molecule, okay. So molecule 4 is braced or is exposed to pressure by the weight of the 3 molecules, 3, 2, 1. So 3 molecules are bracing the molecule number 4. So what can you understand? What can you understand? What about the pressure at this point comparing to this point? Of course, the pressure at molecule number 4 is greater than molecule number 3, greater than molecule number 2, greater than number 1. So as a conclusion, we can say that, which is this is the first one that we can learn from the hydrostatic pressure, is that as we go down in depth for the liquid, this is the depth, or we call it height. As the height increase, okay, as the height increase or the depth increase, we get large or high pressure of liquid, okay. So we get high pressure of liquid. Is that clear? So as we go down, the pressure increase. Why is that? Because the the bottom molecule is exposed to all the top molecules, while the top molecule it's not exposed to any pressure from the bottom ones, okay. Now this is the first point that we need to understand. The first point that we need to understand is as we go deeper, or as the height increase of water, the pressure of liquids increase. This is one. Now what about the second point? Now here I say that I take the condition of this one. Now let me take the condition of this one. Now what is the pressure on this particular molecule? Okay, it is by this molecule. And what about this one? It is by this molecule. What about this one? It is by the weight of this molecule. So each molecule, okay, in the same row or in the specific height has exactly the same pressure. Has exactly the same pressure. So if I am at point 2, all the point through point 2 has same pressure. So this and this and this and this and this and all the molecules along this specific height has exactly the same pressure. So in horizontal line for the liquid, we will have same pressure. In vertical line for the liquid, as we go down, the pressure increase. As we go down or the depth increase, the pressure increase. Again, in vertical, okay, in vertical for liquids, okay, the pressure increase. Sorry, the pressure increase. However, in horizontal, okay, the pressure is same. Okay, the pressure is same. So the pressure at this point is same as this point, same as this point, same as this point. However, for the first one, the pressure is this in this point is smaller than this one, and this one is smaller than this one, smaller than this one, smaller than this one. Okay, so this has the biggest, greatest pressure. This has the less pressure than the greatest, and this has the lowest pressure. Okay, this has the lowest pressure. So this is the uh, number 2, or the let me say the second information that we need to know in hydrostatic pressure. Now the third point, okay, the third point, and this is where we need to know that the molecule can deform, okay, that the molecules in the liquids can be deformed and change its shape. Let's take an example to understand the third one is here. Now someone of you will say that if you have a container, okay, if you have a container and you punch a hole, okay, on the top side of the container, you will see that the liquid comes out of the container with a very low velocity, okay, with a very low velocity. However, if you go to the middle of the container and punch a hole, you will see the velocity increased, okay. Now if you go to the bottom of the container and punch a hole, you will see a very high velocity, okay. You will see a very high velocity comes out. So the liquid comes out with a high velocity. When I say high velocity, it means there is something inside the pressure, inside the container at this point, which just take the chance. Once a hole is punched into the container, it comes out with a very high velocity, okay. So what do you think? It is simply from point 1, okay, that we can say here there is a high pressure compared to this point. That's why the liquid comes with a very high velocity, okay, compared to this one, So why the pressure? Since we punch on the wall of the container, why there is a pressure on the wall of the container? Why there is a high pressure in the wall of the container at this point, and a low pressure in the wall of the container at this point? So let me redraw the molecules, okay, and we mentioned here that at this point there is a very high pressure, okay, in the wall of the container. However, in this point there is a low pressure in the wall of container, and as we go down, Okay, the pressure increased in the wall of the container and to each neighbor molecule. So the molecule will have some pressure along the molecules in their level. Okay, so this one will push and this one will push and the other molecule and this one, they will push each other. Now, what's the reason? Let me rewrite this molecules in other way that will show some water drops, or I will take an example. It's like the water molecules. So this is the molecules. I just take to understand the picture or imagine the picture of the molecules. So these are molecules of for example water, okay, or any liquid. Now let's see here in the first row, okay, which is the very low pressure applied on it. Okay, we can see that the molecule, it has a special shape. Okay, it is as it is, the shape is not changing. Now as we go down, okay, the molecules must be the same. Okay, the molecules must be the same, but see here number two, you can see that this number one pressed or has an exerted pressure on molecule number two. Now what happened to molecule number two? As you can see, there is a difference in shape, right? This is because the molecule, it take the force and then deform its shape, it expands. How to imagine it? Imagine it like if you have a balloon, okay, and fill it with water, okay, and then try to push the balloon from one side, you will see the balloon will try to expand. That exactly the meaning of deformation. So the molecule, okay, or the balloon will deform its shape. حلو، يعني البالون بتلاحظها تفرش، تمام، تتوسع تتمدد أفقيا. So when this molecule, okay, deform its shape, it will exert pressure on the sides of the molecule itself. Okay, so however, it will touch the wall and it will touch the neighbor molecule. Same thing for that molecule, it will touch the neighbor molecule, and the other molecule, it will touch the other wall, and so on. Imagine the picture. Okay, imagine the picture. Now as we go down, the pressure increase, so the deformation will increase and the expansion of the molecule will increase until it become like this. Okay, so this exactly the molecule, it was the same as this one, but due to the high pressure applied on it, okay, it has been deformed and expanded to this side. Now let me show it in other way. So let me clear the writing on the picture, on the figure, and you can see that it was like this. So originally it should be like this. But due to the pressure, okay, due to the high pressure, this has increased. Okay, so it goes out, and this is, it goes out more, and this is expand more. Okay, so as we get more pressure, the expansion becomes larger. Now there is no container that doesn't have walls. Okay, otherwise the liquid will escape. Now imagine, okay, the walls of a container like this one. So here is the walls, and you will see here, I didn't change the picture. You will see that this has exactly touches the wall, and this is imagination picture comes out from the wall, and this is again comes out with a larger area or a larger volume out of the wall. And this is not possible, of course. Okay, there is no way that it will go out. So the wall will try to prevent the liquid from escaping. Now what regarding this one, okay, this extra area, okay, what can we do to avoid it, or what will happen if the wall, now the wall will force this part, okay, will force this part to go down inside. Okay, so what is the reaction from this part? It will generate a very high pressure on the wall, right? Because it has an energy, and this energy cannot be deleted or removed. Okay, so it will generate pressure on the wall, okay, to trying to release the energy. So in order to release the energy, the wall force this part, okay, to go down, and as a reaction, okay, as a reaction, this part exactly will exert a pressure on the wall and on the other molecules on the same side of that one. Okay, so again, this one will exert a pressure on the wall, and as we go up, the pressure is decreasing. So here the wall will give a force, okay, or will force this smaller part to be inside, so it will generate a less pressure on the wall, okay, and this part, it will force this a very small part to be coming inside the container, so it will generate a very small pressure on the container, and as we can see here, it's just touching the wall, okay, so there is not that much pressure. So if you punch a hole here, okay, if you punch a hole here, the liquid doesn't, or the molecule doesn't exert a very high pressure, okay, on the wall, so that the liquid will comes out with a small velocity, okay, so it will come like this. However, if you punch a hole here, okay, there is a higher pressure than the top one, so it will come with greater velocity than the previous one. However, if you punch a hole in the bottom of the container, okay, which has the maximum pressure on the wall, it will come with maximum velocity out of the container. So this is the point number 3, or the information number 3, that we need to understand in the hydrostatic pressure. The most important one is point number 1, which says that as we go deep for the liquid, the pressure increase. So the pressure of liquid increase as the height of liquid increase, okay, or the depth of liquid increase. The point number 2, it says that at a specific height, okay, at specific height, so we are talking about horizontal, so at a specific height, the pressure at all the points for that specific height is same. The pressure at all the points for that specific height is same. Point number 3, we said that as we go down, the molecules will deform its shape, so it will be exposed to high pressure, so it will expand, and this expansion will generate a very high pressure on the walls of the container, okay, on the walls of the container. So these 3 points, it is very important to understand why is that. I will not ask someone to explain the molecules of liquid inside the container and why is that. No, this will make it easy for you to understand what are the factors that affect on the pressure of liquids. Now, the last point, okay, let me go here, okay, and clear the writing, and let me show, for example, here, if this one is water, okay, the water has some mass, okay, so the liquid water has some mass, and just a second, let me double it, okay, just a second. So if we copy this picture and make a copy and then paste it here, so I make a double here, assume it's the same, Let me make it here. So, assume this liquid is water. Okay. And assume this liquid is, for example, mercury. Mercury اللي هو الزئبق. And we know that mercury is much heavier than the water. So one molecule of mercury is much heavier or has greater mass than water. Okay. So what do you think? What do you think the pressure at molecule number 2 here? Since the mass of, let's say that we have the mass of one molecule of water is equal 1. Okay. So it's equal 1 here, 1 kilogram, for example. And the mass of mercury, since we said it's much heavier, we said it's a kilogram. Now, what do you think the pressure applied by this single molecule on molecule number 2? Of course, it will be less than the pressure exerted by this molecule on molecule number 2. Imagine that you are holding a 1 kilogram, a box of 1 kilogram, and the other holding a box of 10 kilogram, okay, on his head, okay. So imagine the pressure. Of course, the one with 10 kilogram is exposed or has greater pressure on his head than you. So what can we extract from this information is that we said that the pressure of liquid has a factor that as we go deep for that specific liquid, the pressure will increase. However, the other factor is the type of liquid. What is the liquid? So, for example, if you have two containers, and these two containers contains two different liquid, and this is liquid 1 and this is liquid 2. As you can see, they have same height, okay, and we said that as we go for more height, the pressure will increase, and they have same height, so they must have same pressure. However, the answer is no, because this liquid is different from the other one. So the other factor is you need to know the liquid that is in the container in order to calculate the pressure. So only two things are required to be understood in the hydrostatic pressure. One is the height of the liquid, okay, because as the height changed, the pressure would change. And second one is the type of the material, okay, which will affect on the pressure of liquid, because different type of materials will have different weights and different masses for their molecules. So in conclusion, the hydrostatic paradox, okay, it says, or hydrostatic theorem, it says that the pressure at a given height or a given depth of the liquid is independent يعني مستقل، يعني ما له شغل، okay, is independent of the shape or the volume of the liquid. This is a very important point. And we'll see example in the next slides. Okay, so the pressure at a given height or depth of the liquid, and if you have same liquid with specific height, okay, it says this liquid is independent، يعني هذا السائل أو الضغط عند هذه النقطة ما له شغل في شكل أو حجم السائل في الخزان. As long as it has the same height and same liquid, the pressure is same, whatever the volume and the shape of the container. Okay, so if you fill a cup by 1 meter of water, okay, and you fill a classroom with 1 meter of water, the pressure will be the same. Even though the shape of the container, we have a cup and we have a classroom, so the container of that liquid is very different, okay? And the volume of liquid, of course, it's different, okay? So the volume inside the cup, it's completely different than the volume of 1 meter of water that covering the classroom. But the hydrostatic paradox said that the pressure would be the same at 1 meter height of water. Okay, so it only depends on the height and the type of the material. So only depends on the height of the liquid and the type of the material. Example for this paradox, yes, here we have 3 different shapes of tanks, and these tanks or containers contain water, and this water is at rest, static, it's not moving. And we're measuring the pressure at the bottom of each of these shapes or these container, and we can find that the reading showing same pressure. Okay, the reading showing same pressure. So pressure at any specific height will be the same for all the tanks. So do not go for the shape, do not go for the volume. Okay, it's not our job. Our job in hydrostatic pressure is to see the height, to measure the height, and understand or know the liquid, the type of liquid. Okay, now what is the formula for the hydrostatic pressure? Of course, we know the general formula of the pressure is weight over area. However, in particular, talking about the hydrostatic pressure, we can say that the formula is equal rho multiply G multiply H. And it is clear because we said that the pressure of liquid depends only on the type of the material, which can be represented or expressed by its density, because we know each liquid has some specific density different than the other liquid. هذه من الخصائص اللي درسناها. And the second one is the height of the liquid. Okay, is the height of the liquid. Okay, so another way of writing the formula is by writing the gamma, okay, as a result of multiplication of rho and g. As we said in the previous lecture, we said that gamma, which is the specific weight of any material, it can be represented as the density of that material multiply the acceleration of gravity. And we said we have difference between the English system and international system in this specific point, especially in the mass and weight. And this should be understood in the previous lecture. So if we trying to write the units of rho in SI is kilogram per cubic meter, which is mass per unit of volume. The unit of acceleration of gravity is meter per square second, and the unit of height is meter. Okay, so by knowing that kilogram meter per square second, which is mg, is equal to Newton, okay, and we can cancel the meter with one of the meters here in the denominator, we will end up by meter square at the denominator. So the pressure unit is a Newton per square meter, which is again Pascal. So we don't change that much. Okay, we don't change that much. The unit is same. Now in English system here we mentioned that a mass of 1 pound mass, okay, will give a weight of 1 pound force. So it will give the same value but with different units. Now, where is the acceleration of gravity? As we said earlier, it's inside this unit. Okay, it's inside this unit. Okay, so bound force contains the multiplication of acceleration of gravity. So that makes it easier for us in English system to say that density of 1 pound mass, which is mass over volume, 1 pound mass per cubic feet, okay, will give a specific weight, which is gamma, of 1 pound force per cubic feet. So whenever you have a density in English system, you will write the same value as a specific weight, but what you will change? You will change only the bound mass into bound force. Where is the acceleration for gravity? Again, it's plugged inside the unit of bound force. So that makes it easier to understand in the English system. However, in the SI system, we need to multiply the rho by g to get the specific weight. So we don't make the multiplication of 9.81 inside the Newton. No, Newton is just a change or a summary of unit. Now, example and exercise. Here in the book, in the textbook at page 71, there is a mistake in solving the example. So the example says, what is the gauge pressure? Okay, gauge pressure, which is one type of the pressure measurement. And he asked, what is the gauge pressure in kilopascal, 1 unit, and the other unit is in Newton per square centimeter at a distance of 1 meter below the surface in water. So we have a container. Okay, we have a container and we have water here. And the water has a height of 1 meter. Sorry, let me rewrite again. So here we have a container. And this container contains the water. And the water level is 1 meter. And he said 1 meter below the surface in water. So this is the surface of water. Okay. And 1 meter below the surface. So he needs the pressure at this point. What is the pressure at this point? As we mentioned that the pressure of liquids, it says as the height increase, the pressure will increase. So the pressure at this point is the highest pressure than any point along the height of the liquid. So it's simply, you can use the formula, okay, and since it says water, so we know that the density of water, so he needs the pressure, okay, the pressure of water, and the formula we said it's a gamma of water multiply G multiply H of water, okay, multiply H of water. So we know that the rho of water is equal 1000 kilogram per cubic meter. So if we multiply 1000 kilogram per cubic meter by 9.81 meter, try to write the unit in your solution, okay? This will make you understand and minimize the possibility of having some mistakes in multiplying or using different units from different systems. Multiply 1 meter, okay? So here we can say that the kilogram meter per second square is equal to Newton, and here we have meter, and with a cubic we end up by Newton per square meter. Let's multiply, and then we will find that the answer is 9810 Newton per square meter, which is equal Pascal, but he said I need it in kilopascal. So we divide by 1000 and the answer is 9.8 kilonewton per square meter, which is kilopascal. Pascal. So we got the same answer. Now try to solve B. Try to solve B. So B, he said that I need the answer in Newton per square centimeter. So he need to convert a 9,810 Newton per square meter into some value in Newton per square centimeter. So try to answer it, okay? You just need to convert square meter into square centimeter and find the result. And see what is the mistake. See what is the mistakes. Okay. Now, the second question, it says an open tank contains a liquid whose SG, which is a specific gravity, okay, equal 1.26. So here we have an SG equal 1.26. And he continues and says, and the liquid has a height of 3.5 meter as shown in the tank. So here the height or the depth is equal 3.5 meter. The question, he said, calculate the gauge pressure at the bottom of the tank. By the way, when someone mentioned that an open tank, okay, an open tank, it means here the top roof is open, okay, and once it's open it means it's exposed to atmospheric pressure, okay, atmospheric pressure. So the pressure at this point, okay, it is the pressure of liquid and there is some pressure on top of it that press it. So pressure of atmospheric and the pressure of liquid. But what is the question here? He asked for the gauge pressure only. And we said the gauge pressure, it is the value that is above the atmospheric pressure. Okay, that is above the atmospheric pressure, which is the value of this liquid. So this make the increase of pressure rather than the atmospheric pressure. So if the tank is empty, there is only atmospheric pressure. But as we put the liquid, okay, the pressure increase. The pressure increase. So this is called the gauge pressure. This is called the gauge pressure. So let's say that we have the pressure formula. It says the pressure of liquid is equal rho of that liquid, okay, and here pressure of liquid multiply G multiply the height of the liquid, okay. This is the gauge pressure. Now how to find the answer? Now do we have the height? Yes, we have 3.5. Do we have G? Yes. Do we have the rho of the liquid or the density of the liquid? No, we don't have it. But do we have something that will lead us to find the density? Yes, we have the SG. Now what is the formula of SG? What is the formula of the specific gravity? We know that the formula of the specific gravity is equal specific gravity of material, since the liquid is type of materials, is equal the rho of that material or that liquid divided by some reference density, which is the water, okay, which is the water. Therefore we can say that we have the specific gravity, we have the rho of water, we know it, 1000, and we will use 1000 kilogram per cubic meter as an SI unit instead of 62.4 pound mass per cubic feet. Why? Because here it says the height is equal 3.5 meter, so it's easier for me to find the density in SI. Otherwise I need to convert the height into feet or inch, whatever the value I will use for the density of water. So I will use the SI unit of water, which is 1000 kilogram per cubic meter. Therefore the rho of the liquid, which is rho of material here, is equal the SG of the material multiply the rho of water. Now let's substitute the value. Here we have 1.26, no units, multiply 1000 kilogram per cubic meter. So the answer is simply, which is the rho of the liquid or of the material, is equal 1260 kilogram per cubic meter. Okay, kilogram per cubic meter. Now take this value and plug it in this formula, and then we can say that pressure of liquid is equal the rho of that liquid, which is 1260, and write the unit, it's better for you, kilogram per cubic meter times 9.81 meter per square second, since it's acceleration, multiply the height, which is the 3.5 meter. Okay, we will write here meter. So as we know that we can cancel meter with this meter and we end up by square, and this unit is exactly equal the Newton. Okay, exactly equal Newton. So if we just calculate the values, we will find at the end the pressure is equal 43262.1 Newton per square meter, which is Pascal. Okay, and we can say it's 43.26 kilo Pascal, which is kilo Newton per square meter. So be careful on using these units, the kilo and these things. I'm saying be careful, okay? Be careful, because most and the common mistakes is in the unit. They know the formula, but they don't know how to use the unit, which unit is better or best to be used. Now the next part, or the example number 3, it says find the absolute pressure for the above example. So here we said it is the gauge pressure, which is only the gauge the pressure above the atmospheric, okay, which represent the pressure of liquids only. Now the absolute pressure, which is the total pressure at the bottom of the container here, okay, the total pressure, it is the pressure of that liquid plus the atmospheric pressure, atmospheric pressure. That's why they call it the total pressure. So the absolute pressure is equal the atmospheric pressure plus the gauge pressure, and we can say that the gauge pressure here we have one value for atmospheric pressure. We say that we know that 1 atmospheric is equal 101.3 kilo Pascal. So here I will write 101.3 and I will write the unit kilo Pascal. In order to add, this unit must be kilo Pascal. Otherwise, I cannot make this operation. Okay, I cannot make this operation. So, do I have the gauge pressure or the pressure of liquid in kilopascal? Yes, 43.26. So, I will write 43.26 kilopascal, which is the absolute pressure. So, the answer of the absolute pressure is equal 144. 0.56. The unit is kilopascal because both units are consistent. Both units are consistent. So the last question, I will give you just the hint Okay, it is a very typical question. Okay, it's a typical question actually to understand the idea of this section. Okay, and I bring it from the textbook, which is the last exercise or the last problems 5.20. Now in this question it says each of the three circular containers in figure 5.13, which is this one. So here we have three circular containers, and or sometimes they say it's cylindrical container. When he said like this, it means the container has a base of circle. Okay, so it's like this. The container is like this. So this base, if you want to find the area of this base, since it's circle, we know the area of circle is pi times the radius square. Okay, the radius square. And if you have the diameter اللي هو القطر، عشان توجد القطر راح تقول انه ايش؟ انه عندي d is equal to r, and that means r is equal d over 2. So if you have diameter, you need to divide it by 2 in order to get radius. This result, you can square it and then multiply it by pi to get the area of this or of the base of the container. Okay, so that's why I put the underline in circular. So to continue the question, let's read. So he said contain a liquid with an SG or a specific gravity of 1.37, similar to the previous example. So from this specific gravity, you need to find the density. And he said, what is the pressure in Pascal gauge? So in unit of Pascal, and he said gauge. So do not include the atmospheric. Since it's open, there is an atmospheric pressure on the top of the tank. So do not include the atmospheric in your calculation, because he asked only about the gauge pressure, not the absolute pressure. So he said, what is the pressure in Pascal gauge acting on the base يعني في أسفل أو قاعدة of each container and the weight of liquid in each container. Okay, so he asked for two things. He asked for the pressure at this point. He asked for the pressure at this point here. So write it P1 is equal what? And here B2 is equal what? Or BA, BB, let us say BA. Okay, so here we'll write A instead of 1, since the figure is A. And here instead of 2, we'll write B. And here he said, what is the pressure at BC? So you need to find the pressure at each point. Okay. As you can notice that all the containers has what? You can notice, okay? And the weight, okay, in order to calculate the weight, you need, there is two things I will mention here, and then I will let it for you as a homework to answer. Okay, and if you answer it complete, we will discuss it. Okay, but the last chance is on Sunday. If you want to answer it complete, submit it before Sunday, and you will get a bonus. You will get a bonus mark, but complete solution and draw a correct one. So one thing I will tell you, that volume, if you want to calculate any volume, you will say volume is equal area, any area, multiply height. المساحة في الارتفاع. الحجم يساوي المساحة في الارتفاع. And the weight, regarding the weight, we have different formula for weight, or includes weight. We have weight is equal mg, and we have density, specific weight is equal weight over volume, and we have rho is equal mass over volume, and you can take this mass, put it here, multiply by g to get the weight. And yes, these are some formulas that you can solve the weight with. Try your best, okay? It's easy, but it's typical. It's typical. So those who will solve the question, it means that they understand the hydrostatic pressure. They understand the hydrostatic pressure. There is another point, okay, I need to say here, is here, yes. So here I mention one point exactly at this notes. I said, as we know, pressure is equal weight over area. This is the general formula for the pressure. And I ask you that, can you find how the formula B is equal rho GH, okay, which is the special formula for the hydrostatic pressure and the pressure of liquids. I ask you, how can you find how this formula is derived from the main formula? Of course it's derived, okay? The scientists, they don't put this formula from their heads. No, they use the general formula. The main formula of pressure is weight over area. So they did something on this weight over area in order to find or derive يشتق, okay, اشتقوا قانون جديد, and they call it hydrostatic pressure. Knowing that volume is equal area multiply height. Since I mentioned this one, knowing that volume is equal area multiply height, it means it's used somewhere in the derivation. So this not included in your course. I mean, you will not be asked in the exam this question, but those who can find how they derived or the exact derivation from the weight over area, what they did to reach rho GH, okay, again there will be a bonus. So that's all in our lecture. So we conclude and study the 3 sections as we mentioned, okay, in our outline, and we studied the pressure, what is the pressure, and how what is the pressure formula and the units, and what's the principle of pressure. We take some concepts of pressure, basic concept, and we understand the relation between the area and the pressures, and some application where we need high pressure and others where we need low pressure. In the second section, we mentioned some different types of measurements for pressure, and we mentioned 6 types. The third one, we mentioned one type of pressure. It's called hydrostatic pressure. If we want to measure the pressure of liquid, and this liquid must be at rest or static, so a special type of that pressure can be used. And we conclude that the pressure of liquid is independent of the shape and volume of the container and the liquid, but it depends only on 2 things and nothing else, which is the height of the liquid and the type of the liquid, and can be represented by the density, okay, because the density is its properties for that material, and each material has different density. So that's all in our lecture. Hope inshallah it's easy. Now we start on understanding the concepts. So that's why I said in the first 2 lectures it's very important to understand before reaching this lecture and starting this chapter. The things will be entertainment, okay? So you will be entertained if you understand. So the physics, if you try to understand it, okay, it's an entertainment, by the way, but if you miss something, it will be a nightmare. Okay, it will be a nightmare for you. Hope, inshallah, all of you understand. And if you have any questions, please ask. Okay, please ask. Do not accommodate the difficult things or or the misunderstood things on your head that will affect on the next lessons. So thank you all for listening, and have a nice weekend, and see you inshallah in the next week.